Example 8.8. Let's read the problem together. A lossless transmission line of length 0.434 lambda and characteristic impedance of 100 ohm. This is RO. Let me write. RO is 100 ohm, is terminated in an impedance of this one. This is ZO. Okay. So let's try to draw the circle. It would be better to understand the problem. Let's say this is the generator. This is transmission line, and we have output impedance. So it says the transmission line, the length of the transmission line is 0.434 lambda. And this is our output impedance. I am using the touchpad, so it is taking a while. Okay. So the first thing, it is asking the voltage reflection coefficient. Okay. So how can we find that? Let me show you here. Let's say this is our WSR circle. To find the R value, reflection coefficient, we need the ratio. Okay, this distance, ratio of this distance to this big one until the inner circle here. So the reflection coefficient is the ratio of this length. Okay, so for that we need this WSR circle. After then we can find the ratio. Let's go back. To find this we need Z output normalized. ZO normalized. Okay, we need to normalize this value to find that point on the Smith chart, because we cannot find these values of the Smith chart. So to normalize this, by the way, this is 2, not 1. Okay, to normalize this we need to divide this value by RO. We need to divide this by RO, which is 100. Okay, here it is 100 ohm. So if we divide it, it's simple. 2.6. If we divide this by 100, 2.6 plus j 1.8. 1.8 ohm. So now we can find this point on the Smith chart. 2.6. The real value is 2.6. 2.8, this is 6. So here is the real value, this one, and plus j 1.8 imaginary value, 1.8, this one. So intersection point is here. So this is our Z out normalized value. Okay, normalized point here, the intersection. So let's take, first of all, I will delete this. Okay, this is our Z output normalized point. Now, what is this? 297 is our radius. What about the diameter? Diameter is twice of it. Let me multiply. Okay, it's about 595. The diameter of the circle, 595. Let's align it in the center. Now, okay, it's fine. This is our WSR circle, not WSR circle. Voltage standing wave ratio, SWR. Now we are looking for this reflection coefficient. So as I told you before, the length of this one, and we need the length of this one. So we need these two to find it. Okay, we know this length of this in pixel. What was it? Let's say 297. Okay, and we also need okay, what about the length of this? Okay, now the ratio, let me divide this value. It is giving me 0.6. Okay, 0.6. By the way, this is the magnitude. Also, we need degree. The Smith chart is already given the degree. This here. This is the degree values. It's 20 degree here. We can say, since it is increasing by 2 to 4, 6, 8, so I can say 22 degrees here. 20 degrees. So this is our reflection coefficient. Let me write it here as well. 22 degrees. Okay, we are done with the first question. So B, where is B? The standing wave ratio. Okay, voltage standing wave ratio. This is quite simple and we have found it already. To find the voltage standing wave ratio, so we are drawing the circle, and the right side, the values on the right side, which is 4, it is directly given the voltage standing wave ratio. So this 4 is our value. Let's say standing wave ratio, it is 4. This one. Okay, what about C? The input impedance. Okay, this will take a little while, I guess. Okay, so input impedance is here, as you know, Zi. Okay, we know the length here, and we know the output point on the Smith chart, and we know the length, so we can easily find this. Okay, also let me tell you, we know this point, we know the point here, then we need to go towards generator. So it means on the Smith chart we need to travel in the clockwise direction. So this was our output normalized value. So from this point we need to travel in the clockwise direction, and the lambda value, this one. Okay, lambda. But we need to find this point here in the lambda values place. Okay, let me take this. They need to intersect, they need to be on top of each other. So okay, that's fine. Now we need to travel in the clockwise direction and 0 point. Okay, and we are here 0.22. 20 to okay, it is given 4, 5, 6. No, after traveling this much we will be on this place. Okay, so we basically need to travel. We are here on this point and we need to travel this much, so we will be here on this point. 0.154. One five two four, this point. Okay, let me duplicate this arrow, then take it also here. Okay, it is quite alright. So the intersection of this arrow and SWR circle, so the intersection is our Z input normalized point. Okay, so Z input normalized, this point. So but it is asking for us not normalize the input impedance directly. So let's find this point, then we can easily go to Zi. Okay, so let's read the values of this point. The real part is the circles. The circles are given the real part, so let's follow this one. Okay, 0.7 real value. Let me write it here. This is normalized. Real value is 0.7. What about imaginary value? It is this one. 1.2 plus J 1.2, because ohm. Okay, this is plus J because, let me show you, we are using the upper side of the Smith chart. We are taking plus J. If we were using the 1.2 at the bottom of the Smith chart, so that time it would be minus J. But now it is plus J 1.2 ohm. This is our normalized Z input. What about input impedance directly not normalized? So for that we need to multiply by RO this value. Here we divided, but now we are doing the reverse. So we need to multiply this value by RO, and which is 100. So it becomes what? 70. If you multiply by 100, this becomes 70 plus J plus J 120. Yeah, ohm. Okay, this is our input impedance, but I would like to take it here. Okay, so input impedance. What about the last question? It is the location of a voltage maximum closest to the load. Okay, Vmax point is here for impedance chart. Vmax here, this point on this blue circle. This is the Vmax point for impedance. Okay, then it is asking this distance here to here. Okay, so we can easily find it. We know the value of this point Vmax, which is 0.25, and also we know the value of this point 0.22. If we subtract this value and this value, we will subtract this value from this value because it is increasing. So if we subtract, we will easily find the answer. 0.22. This time we need to subtract. 3, 0, and 0. So this is the answer. Let me write it here. We can say D distance to Vmax point from load, it is 0.03 lambda. Okay, so these are the answers, and this one is ohm. Okay, so that's it for this video and for this question. Thank you for watching. Have a good day.